also put my own camera off to make the film slightly smaller. Okay, there are no questions, right? I hope about the function space representation thing. And let me start the presentation. Okay, so we defined the vector space, the function space representation the last day. Remember, the basic idea was, suppose you have a vector space V on which you have a representation already. That is, there is a representation L such that for all G, there is an LG which is a map from V to V, and these LGs obey this rule. LG1 times LG2 is LG1 G2. And what we said is, suppose we have a now from this vector space V, we can define a space of linear functions on V. Oh, sorry, not linear functions on V. Linear space of functions on V. We can come up with some notation for that. Let's say curly F maybe, which is a space of functions on V, and this is a linear vector space, or to be more precise, can be made into a linear vector space by giving definitions of how to add functions, how to multiply functions by scalars, and so on. Okay, I would suggest that one of you at least keep your mic unmuted and respond from time to time, because now I can't see anybody of you and I don't even know whether I'm still connected or not. And today my connection is a bit spotty, so I'm a bit scared about that. Just hope somebody heard that. No?
Sir, you're audible. Yeah.
No, it's not a question of my being audible. It's a question of whether I get disconnected and then I keep on talking because I don't realize I've been disconnected. Anyway, so I need periodic feedback. Even if you don't feel like it, you have to keep on telling me that you heard me from time to time. Not always, hopefully.
Yes.
Okay. So then we say that for every such G, given we have an LG, you can define RG, a representation on the function space, which changes the function f to another function RGF. Now, how do you define the new function? You tell me what it does to a vector in the vector space capital V. And what does it do? You say it does this, LG inverse acting on V. We justified why we need to do this the last day. That is, this actually ensures that RG1, G2 will be RG1, RG2. So we will have a representation in this new vector space, the linear space of functions on V. Okay, now what I want to do first is that I want to talk about an example of this in action so that we can see that this actually works and gives you a representation. Now, I will not carry out the full calculation because it's sort of lengthy and boring after a few steps. And of course, the boring stuff is better done by the students. So you're the ones who have to do it in the long run. But let me just point out that what we are going to talk about is basically we'll talk about the group of symmetries of what I think is a possibly good equilateral triangle now. Okay, so what are the symmetries here? The symmetries, of course, are doing nothing, then reflecting about this median. Okay, let me just get rid of all these irritating looking lines. Maybe I will just use a slightly different color here. Oh, I got rid of too many lines. So I have this equilateral triangle. Let me put some labels on the vertices. These are A, B, and C. And now what I want to do is label the symmetries that you have. Maybe I will just use a dashed line for this. So reflection in this vertex, this median will be a symmetry. Reflection in this median will be a symmetry. And reflection in this other median, third median, will also be a symmetry. In addition, there will be two rotations. I'll draw it this way. I keep on forgetting that this is not an ordinary pen. But anyway, let's go back to this. So a 120-degree rotation is a symmetry. A 240-degree rotation is a symmetry. So there are 6 symmetries in all. 3 rotations, do nothing, rotate 120 degree, rotate 240 degree, and 3 reflections in the 3 medians A, B, and C. So just to label, this is the median A, and reflection in this median we will call the group element A. This we will call the group elements B. This we will call the group element C. This 120-degree rotation we will call D, and E is already taken for the identity. After all, that's the German ein. So we will use F for this other rotation. So these are the 6 operations which form the equilateral symmetries of an equilateral triangle, assuming, of course, that you cannot flip the triangle over. That is, that maybe we are in a 2-dimensional world, there is no third dimension, or even if there's a third dimension, maybe the 2 faces of the equilateral triangle are colored with 2 different colors. So you can't see. You can't flip it around. If you flip it around, it's not a symmetry any longer. Okay, so these are your 6 symmetry operations. And so let's list them: A, B, C, D, F. And of course, there's the identity. This set forms our group of symmetries of an equilateral triangle. And this happens to be isomorphic to the group of symmetries, group of permutations of 3 numbers, S3. Can anybody explain to me why this has to be isomorphic to S3? You can of course show that this is isomorphic to S3 by constructing an isomorphism. I'm asking you to show why this has to be, or just argue why this has to be isomorphic to S3. Anybody?
Any permutation would be just all in vertices exchanging. So it's kind of like permutations of 3 objects.
Okay, good point. The point is you should really look at that. Instead of looking at the whole triangle, you can just look at the 3 vertices. And any of these operations just permute the vertices. Well, not only that, all permutations are possible, right? There are only 6 possible permutations, and you can do all of them by doing E, A, B, C, D, F. In fact, that's an important point, because after all, if you had a square that has 8 symmetry elements, that group, of course, is the group of symmetries of a square is definitely not S4. S4 has 24 elements. Why in a square, for example, if you have A, B, C, D, the vertices, a permutation A, B, D, C is of course possible, but it's not possible to change A, B, C, D to A, B, D, C. Just flip 2 of the vertices, adjacent vertices, not the other 2, by any rigid operation whatsoever, right? You cannot rotate, reflect to do this. Which is why the set of symmetries of a square definitely has less elements than the set of possible permutations. But the triangle is a bit different. Okay, now that we have all this, let us now try to first set up a vector space representation as operator representation or other matrix representation by choosing a basis on this. So that's a sort of trivial, and what I need to do is definitely, okay, maybe I need to get rid of some of this extra stuff here. So I hope, okay, let me just keep this anyway. Let's try to see, let's use a thicker line, and maybe, oh, why is this so sluggish today? I just got thrown out from my own account. It's not, I didn't get logged off, or I didn't lose connection. It seems that the Zunal application has some bug which sometimes tries to throw you off completely. So I will have to start again, I guess. I'm still presenting, right? It's still being recorded. So you can see this, hopefully. Yes, you can see this, right? Although I have to start all over again, and let me just do it a bit more quickly this time. Okay, let's see. This is a equilateral triangle, or my attempt at an equilateral triangle. And then what I want to do is draw a basis for the vector space here. The vector space is, of course, the underlying vector. Yeah.
Sir,
I can't see
see your
anything.
screen.
You can't see anything. Okay.
No,
That means my presentation has gone off now. Let's hold on. Okay, now you can see something, right?
yes.
So you should be able to see the triangle now. I had to start all over again anyway, but still, let's see. What we have here is we have this plane R2 on which the group, which by symmetry group of the equilateral triangle, which I'm just calling S3 for want of a better name right now. As I said, it is isomorphic to S3. But the operations here, of course, are not permutations, they're reflections and rotations. And what we are going to talk about is what S3 does to R2. We know what S3 does to R2. Elements of S3 rotate or reflect in R2. But in order to get a matrix representation of that, which I will need before I can go over to, or an operator representation of that, before I go over to this function space representation, I need this one. So let's just try to construct this. So I will have to choose a basis first, and the obvious choice of basis is an orthogonal basis E1, E2, which I'm choosing. Okay, now remember the labeling was, this is the vertex A, this is the vertex B, this is the vertex C. And what does the identity do to E1, E2? That's the easiest one to get through. So E, of course, maps E1 to E1, E2 to E2. So there's a map at the operator level. This, of course, is what the linear operator corresponding to E does to this element. So this is LE. Yeah. We can, of course, also get the matrix representation, which we are calling DE. And that's trivially 1, 0, 0, 1. But let's get a bit more, bit non-trivial here. A. What does A do to E1? Okay, now please keep yourself unmuted at least so that you can answer. What does A do to E1? A, remember, is reflection in the median passing through A. The vertex A. This is a small a. The reflection in this vertical median. What does it do to E1? It maps E1 to?
Minus E2.
Minus?
Minus E1.
Minus E1, right. And E2 to?
It doesn't change it.
So it gives you E2 back. So that's, of course, minus E1 plus 0 E2, and this is 0 E1 plus 1 E2. So you know the coefficients, and dA, the matrix, will simply be minus 1, 0. You write the coefficients minus 1, 0 in this line vertically, that is, you write them down a column, and you get 0, 1. Of course, in this case, column row doesn't matter because you have a symmetric matrix, but you will not always get a symmetric matrix. So this order is important. Now let's talk about a slightly non-trivial one, which is B. And just to remind you, B is this thing. B is reflection. Oops. I forgot that I'm using a line drawer, so I can just. B is reflection in this medium. So can anybody tell me what this will do? What will it do to E1? So this is slightly more tricky. But what is the angle which E1 makes with the median?
30 degree.
I couldn't hear you. 30 degrees. Is that
30 degree.
30 degrees, right? So after reflection, it will make an angle of 60 degrees. The reflected version of E1 will make an angle of 60 degrees with E1, right? Because this angle is 30 degrees. So if you reflect in this, you will get an E1 prime, which will be in this direction, making an angle of 60 degrees total with E1. And that, of course, means that it's going to be half E1, that's cos 60 degree, plus root 3 by 2 E2 sin 60 degree, right? Is it okay? And what about E2? E2, well, you can easily figure it out by just the fact that E2 has to be perpendicular to E1, even after the rotation. So the root 3 by 2 and half will swap, and there will be a change of sign, right? That's the easiest way to talk about a rotation through 90 degrees. There will be a swap of sign and interchange of the coefficients. You all know this, right? But the only thing you have to do is figure out which one will be positive. And that's easy. If you reflect E2 about this axis, it's easy to see it's going to go down. So E2 will, the second x component will be negative. So it's easy to say this will be minus half and root 3 by 2. Right? So what is the matrix corresponding to this? You take take these coefficients half and root 3 by 2, write them down. Write them down the column, and take the other two coefficients, root 3 by 2 and minus half, write them down the second column. So that's your representation matrix for B. So all this has nothing to do with the function representation. It's just leading up to that. And well, you can keep on going anyway, but I will just stop here because the rest of the things you can fill up. As you can see, once you have got square roots of 3 and so on, things are getting a bit tougher, and once things get tough, I can always leave it to the students to work them out. But now what we are going to talk about is how to use this representation, which we are going to assume we already have worked out. So I know DE, DA, DB. Yeah, I already know 3 of them. I also know DC, DD, and DF. So once I know all this, how do I work out the representation that follows from this one in the function space? Now, I'm not going to talk about what happens on the entire function space. Let's be a bit selective. Let's talk of the space of all homogeneous quadratic functions. That is, functions of the kind ax square plus bxy plus cy square. Remember the vector v, of course, this is a map. This is a function which will map v, which is of course x e1 plus y e2, to this function, this value ax square plus bxy plus cy square. Okay, so it's a map from the space v to the space of real numbers. Okay, what is the dimensionality of the space of functions? Yeah, there's a three-dimensional function vector space with an obvious choice of basis. Let's say f1 is a function which maps v to x square. f2 is a function which maps v, let's say, to y square, and f3 maps v, let's say, to xy. So any function like the one which I have written here is simply AF1 plus BF2 plus CF3, because when it acts on a vector V, it's going to give you A times F1 of V, which is, this is how a linear space of functions work. That's how you define AF1 plus BF2 plus CF3 in the first place, and that will give you AX square plus BY square plus CXY. Right? So it's easy to see that F1, F2, F3 form a basis for this particular vector space of homogeneous quadratic functions acting on the vector space capital V. Okay. So now the question is, because it's a 3D vector space, I should be able to find the 3 by 3 representation of my group S3 on this using the representation that I already have, the two-dimensional representation that I already have. So once again, let's do the simple things. The simplest one is the representation for the identity. So what does it do? It acts on functions. So the question is, what does it do to every function? But as always, because the functions form a linear vector space, all we are only asking is what does it do to the basis vectors, in this case F1, F2, F3. So just to show you, I'm pretty sure all of you know what will happen here, right? REF1 has to be F1, but how do you prove this? This is just a way of reminding you of what this is really doing here. This is really by definition, what is REF1? It's a new function. What is it supposed to do? It's supposed to be give you the same result as F1 does when evaluated on LE inverse V. Right? That's the way the function representation is defined. But what is LE inverse V? LE inverse is of course the same as LE, and LE acting on V does nothing. So this gives you F1V. And since this is true for all vectors V, we are going to say REF1 is F1. And no prizes really for working this. Hey, my Zuna died on me. I'm still presenting, right?
Yes, sir.
Okay, so since I think it's realized that I was doing something very trivial and stopped me from doing that. I've got to figure out whether this is a feature or a bug, but okay, so this is what it does to the functions, and so obviously this is going to give me a three-dimensional representation for the identity, and again no prices for guessing what this one is. This is simply 0, 1, 0, 0, 0, 1. So rather trivial. I agree, this is really not worth spending much time on, but if remember there are 5 other group elements. So let's look at what RA F1 will do, or F1, F2, F3, RA Fi will do. What does RA Fi do to V? It gives you Fi, the ith function basis vector, at on LA inverse V. But LA inverse V is same as LAV, right? Because that, okay, let's do it in steps. This is LA's inverse is the same as L of A inverse. That's a basic property of representations. And since a reflection is self-inverse, it's the same as V. So if V is XE1 plus YE2, then LAV, what will this be? LA, remember, is an operator which acts on vectors, right? Now when you write this vector V in this form, E1, E2 are basis vectors, they are vectors, X and Y are just numbers. So LA will just skip over the X and the Y and go and hit E1 and E2. And if you remember, what does LA do to E1?
Sign changes.
The sign changes, and so the resulting thing here is minus X E1 plus Y E2. So LAV is a new vector whose components are minus X comma Y. So what does RAF acting on V, F1 acting on V give you? It actually gives you F acting on minus X E1 plus Y E2. F1, sorry. But remember F1, F2, F3, we wrote them down. F1 is X, F1 gives you X square, F1 acting on V, F2 acting on V gives you Y square, F3 acting on V gives you Z, XY. Where, of course, XY were the two components of the vector which you were feeding to the function. So this is going to give you minus X whole square, which of course is X square. And that's F1V. Again, this is true for all V, which means you end up with RAF1 is F1. RAF2? Okay, what will that be? You don't have to really write out everything. What is RAF2? You can immediately see. RAF2
Minus F2.
is going to be?
Minus F2.
No. F2 is Y square.
It's going to
It's
be
going to be F2. Right? It's going to act on this vector minus X E1 plus Y E2. Take the second component, whatever that is, square that. Look at Y square, which is of course F2 again. F2 acting on V again, right? It's RAF3, which will take the first component and the second component and multiply them together. It will give you minus XY acting on the vector V, which is not what F3 gives, which is what minus F3 gives. Right? So the three-dimensional representation we will get for A is 1, 0, 0, 0, 1, 0. So far, it's exactly like the identity. 0, 0, minus 1. So that's your 3D representation, which comes from this particular function space representation. Okay. So these two were rather simple. Let's at least try working out RB. And for this, of course, what we will need is LB inverse acting on V. But what is LB inverse acting on V? Is the same as LB acting on V, right? Because B inverse is the same as B. And so if V were X E1 plus Y E2, then this will simply be, what will this be? X times whatever LB does to E1, and we figured out what it does to E1 a while ago. Okay, unfortunately, I can't look at the recording right now. So either you work it out again, or it's E1 plus root 3 E2 by 2. That one was slightly easier. That's Y. I hope I'm doing this right. Root 3 E1 minus E2 by 2. It's going to give you root 3x. Oh, sorry, not root 3x. Where did I get that from? It's going to give you x plus root 3y by 2 E1 plus root 3x minus y by 2 E2. By the way, the matrix was half root 3 by 2, root 3 by 2 minus half, right? And notice that if you fed this to the vector xy, or rather fed the vector xy to this, you will get these coefficients. That's exactly how the matrix representation is designed. When you are defining it through the action on the basis vectors, and there you have this rather strange JI thing, the interchange of the two indices. But that actually ensures that when you think of it as acting on the column vector produced by the components, it gives the right transformation of the components by the ordinary rules of matrix multiplication. That's exactly, so that is the one which you are usually used to seeing before you learn about linear algebra and stuff like that. But the two are consistent ways of looking at things. So now comes this RB F1 acting on V. It will actually be F1 acting on this vector. We are supposed to take the component of the first component, the coefficient of E1, and square that. You are going to get 1/4 x square plus 3y square plus 2 root 3 xy, right? And that's of course the same as 1/4 f1 plus 3/4 f2 plus root 3 by 2 f3 acting on the vector v. So what is RBF1? RBF1 is more complicated than the ones we have seen so far. It's 1/4 f1 plus 3/4 f2 plus root 3 by 2 f3. Okay? So that's just one part of the calculation. I've got one column of the three-dimensional matrix D3, right? Yeah? So can we quickly do the rest? I need a new page. And just to remind you, LB inverse V is, as you worked out right now, and so RB acting on F2. Okay. I think you should be able to tell me what the answer is without really having to go through the intermediate steps. What is this supposed to do? It's supposed to apply F2 on LB inverse U on this vector. And of course, what does F2 do? Take the second component and square that. So what you are going to get is 3/4 F1 plus 1/4 F2 minus root 3 by 2 F3 acting on V. So RB F2 and RB F3 V. That's again slightly trickier. You have to remember what it does is takes the two elements, two components, multiplies them together. So it's going to multiply this one with this one. And so you're going to be left with, yeah, hopefully I'm doing this right, root 3 by 4 F1. That's ultimately this is going to act on V. So when I say root 3 by 4 F1, I mean that when I multiply them out, I'm getting root 3 by 4 x square minus, not plus, minus root 3 by 4 F2, and then we get a product of xy type, so that's minus 1/4 plus 3/4, right? So plus half F3. I hope I've got this right. So now this is RBF1, RBF2 and RBF3. So I get 1/4. The matrix I get is 1/4, 3/4, root 3 by 2. That's from this line. That's the first column. The second column is 3/4, 1/4 minus root 3 by 2. And the third column is root 3 by 4 minus root 3 by 4 half. So this is your three-dimensional representation for the group element B from this particular function space representation. Okay. Now I've of course not completed the whole calculation. I'm pretty sure it's going to get very boring if I did all of this in front of you. But I would urge all of you to actually go and carry out this full calculation because it's going to be useful. As training also, it's going to be useful later on. So even for applications, this particular representation actually will come in handy sometime in the future. But what is important is Okay, there's only one tricky thing here. So far, all we have done is we have applied. We were supposed to apply LG inverse on V, but in all the three cases we have seen so far, we have ended up actually applying LG on V. Why? Because in all these cases, the group elements E, A, and B were all self-inverse. Inverse C is also self-inverse. Reflections done twice cancel each other out. But the thing will be different when you will try to find out representation for D and F. Those are going to be more tricky because, not really much more tricky. All that you have to remember is LD inverse is actually LF and LF inverse is actually LD. So that's the only tricky part. Otherwise, this is pretty straightforward. Okay? Fine. So this is the sort of the boring explicit calculation part. Now we go back to the theory and we talk about a very important representation called the regular representation of a group. Now this is one representation which every group comes equipped with. Now, of course, you should realize that when you say a representation, what you really mean is a homomorphism from the group to a set of automorphisms on some vector space, right? So, once again, am I still here? Yeah.
Yes.
Okay. No, that might sound a bit boring that I keep on repeating that, but unfortunately I can't see anything right now. So I'm just hoping that I'm not speaking to the wind somewhere. Okay, so as I said, you need a group G and you also need a homomorphism from the group G to some subset of automorphisms on a vector space V. So representations usually require not only the group but also a vector space, right? So something external to the group. But what if the group itself is a vector space? Okay, that's sort of absurd, right? Group elements cannot be added or multiplied by scalars. There's only one operation on a group, which is you multiply elements or you compose their elements together to get new elements of the group. That's it. There is no additional structure which makes it a vector space. I'm talking about a general group. All possible groups, they don't form vector spaces anyway. You talk of rotations. What do you mean by addition of two rotations? Or multiplication of rotation by 2 or 7.5? However, there's one very nice thing. All you can do is I can form an algebra called the group algebra out of every group. So every group has a corresponding group algebra. So what is an algebra? An algebra is a technical word which essentially means it's a vector space with a multiplication. So in addition to having a vector space defined, you also have an additional operation which is multiplication of its own elements. And it becomes an algebra if it obeys some rather obvious properties like distributivity, etc., etc. So the group, of course, already comes equipped with a product. The question is, where is the vector space? The answer is you make the group a vector space. How? You just define so what is alpha G1 plus beta G2? The answer is it is alpha G1 plus beta G2. Where G1, G2 are here, G1, G2 are group elements, alpha, beta are serial numbers. So what you do is you define your elements of the group of the algebra to be of the form alpha I gi, I going from 1 to n. I'm still talking of finite groups. GIs are all the group elements actually, and alpha i's are real. So does this make any sense? This is like adding apples and oranges, right? And at least English tells you that you should never add apples to oranges.
Sir, what does the plus mean in this scenario? Because group elements can have a product defined in between them.
Right.
Uh,
Good. So what does the plus
so
mean? That's the question. What does it mean when if one group element is an apple and the other is an orange? What does it mean when you add an apple and an orange? So let's answer that question first. Does it make sense to add an apple and an orange? The answer is yes. What do you do when you add 3 apples and 2 oranges? What do you get? What do you get? You get 3 apples and 2 oranges. That's it. And okay, so you get 3 apples and 2 oranges. What does a plus mean? Nothing. The fact that you have 3 apples and 2 oranges. But there can be another element of like this, 2 apples and 5 oranges. Can you add these two together? You have one bag with 3 apples and 2 oranges, another bag with 2 apples and 5 oranges, and you put the contents together. What do you get? You get 5 apples and 7 oranges, right?
So here by plus you just put different elements like tuples or something like that, right?
I don't care what the plus means. It gives me a perfectly good look. The plus in any situation is something you define. Okay, it's really not God-given. It's something which a mathematician has to define. Here, the definition is you just put them together. End of story. But what is important is this actually, because you're allowing not only plus but also multiplication by scalars. Now you have a perfectly good vector space. If I have an element sigma alpha I gi, that's one element. There will be another element sigma beta I gi, sum over I. Can you multiply them together? Well, that comes later. Can you add them together? The answer is of course you can. The summation will be alpha I plus beta I gi. Right? Just like when you add the apples, you know how to add apples to apples, right? You may not know how to add apples to oranges, but you do know how to add apples to apples and oranges to oranges. And that's all you really do. You just add the apples to apples, add the oranges to oranges, and just say that, okay, I have 5 apples, 7 oranges. Same here. Similarly, can you multiply this alpha I gi by a scalar lambda? Of course you can. And I will urge you to check that once you do this, this satisfies all the necessary conditions for a vector space. And that's sort of trivial, but you should actually check the 8 defining conditions anyway. So what do you mean when you add, say, we had this group E, A, B, C, D, F, 3 rotations, 3 reflections, E, D, F, 3 rotations, 3 reflections. So what is the general element for this? General element for this will be mu1 E plus mu2 A plus mu3 B plus mu4 C plus mu5 D plus mu6 F. What does it mean? What does it mean as an operation? Nothing. It doesn't mean anything as an operation, and I don't care. I mean that this is a perfectly good element and I can work with it. I can take 2 such elements, add them together. I can multiply an element by a scalar, and I have a perfectly good vector space, which has a perfectly obvious basis. What's the basis? Yeah?
E, A, B, C, D, the group elements itself.
Yeah, the group elements themselves, they form a basis, because every vector element has been written as an expansion in terms of them. Of course, you could use other combinations of the group elements, linear combinations, But you don't have to. You just have one presented to you, the group elements, and you just work with them. So they are your bases. Okay? Fine. Now, you can also define multiplication of elements, and the basic thing is this group algebra, just having a vector space and a product does not make something an algebra. What makes it an algebra is that the product has to distribute nicely over addition, which I can do by definition. I can simply say something like this. Say I have E plus A into B. That's BE plus BA. By definition, and BE is an element of the group, BA is an element of the group. Done. That's your result. Okay, so this is just a this will give you a perfectly good 6-dimensional vector space which has a perfectly good multiplication of elements defined among them. If you multiply two elements, you are going to get another element of the group and so on. Okay. So why is this useful? It's useful because, first of all, every group comes with this algebra automatically. You don't have to go looking for it. There is no external vector space which you're looking for. The vector space is provided by the group itself. Okay. And as such, it automatically has a representation on it. So let's first talk about the representation at the level of operators. So for any group element G, there has to be an LG, an operator, which acts on an arbitrary vector on this space. And what you want is that this LG, this map L, which maps G into LG, has to be a homomorphism. The first LGV has to be some element of the vector space, and you define it. This is a definition. You define it by this. Okay? Is it okay? You just say, take your vector V. The vector V, remember, is some linear combination of the group elements. Hit it with G inverse from the right. That means you're going to essentially take the same linear combination of each of the basis vectors hit from the right by G inverse. And that will give you the result of LGV. Now, you should not doubt whether this is a map. Okay, and that this is a linear map is also trivial. That's trivial from the way you define G inverse to distribute, right? If you apply LG on A1 V1 plus A2 V2, that's A1 V1 plus A2 V2 G inverse, and by our definition of the way group element product distributes, that's the defining property. This has to be A2 V2 G inverse. So that's A1 LG V1 plus A2 LG V2. So these are sort of trivialities. The question could be, of course, why VG inverse? Why not GV? Why not something else? Or why not VG? And the answer, of course, one way of answering that is, let's look at what LG1, G2 is. After all, we want this to be homomorphism, right? By definition, this has to be V, G1, G2 inverse. And that's V, G2 inverse, G1 inverse. So you can think of, now you can use associativity. Think of this. And what's VG2 inverse? That's really LG2 V. This hit with a G1 inverse. But that's LG1 hitting LG2V. But that's the same as LG1, LG2. That by definition is LG1, LG2, right? The product of two operations is doing one after the other. So we immediately get this all-important result that LG1, G2 has to be LG1, LG2. The inverse here has actually ensured that. Okay? So what we end up with is L is a homomorphism. From G to a subset gamma of the automorphisms on the group algebra. Is this clear so far? Now I'm really beginning to worry whether I'm here. Am I?
Yes.
Okay.
Yes. Can you repeat the last sentence?
Which last part?
L is a homomorphism from G to automorphisms from automorphisms
Look,
of the
so
algebra.
LG, what is this? It's a map from which carries a vector V to another vector. Now, what is this vector? This vector is an element of the group algebra A.
Yes.
Okay. And
Yes.
so LG basically is, and you can easily check. Okay, I didn't really go through the proofs, but you can easily check that there is a non-singular map and so on. So this really LG is this LG, the result of L acting on G. There are two different things here. One is L, which maps G to LG, and LG itself is a map which acts on vectors to produce new vectors. Okay, so the homomorphism, of course, is L because it acts on every group element of capital G to provide an LG which is a member of gamma A. Gamma is simply the group of automorphisms of the vector space. LG is an element of that. L maps you from G to LG, takes you from small g to LG and takes you, domain is capital G, its codomain is a set of all automorphisms on the vector space of the group algebra.
Okay.
So you have to be careful. There are different maps at work here. When you say map, LG itself is a map, GL is also a map, but different domains, different codomains. You have to keep that in mind. Okay, but what is the regular representation? Well, one, of course, great thing about it is that it comes with the group always. Every group comes equipped with the with this representation. And so if order of G is n, then regular representation is, well, it's a representation on a, well, on a vector space whose dimension is right. So if you have a group of 6 elements, the regular representation will be a 6-dimensional representation, right? Why? Because your vector space is 6-dimensional, because just as the example that we talked about, all vector space elements are combinations of the 6 elements E, A, B, C, D, F. So if a 6-dimensional basis, you're done. Okay. So how do you find out the corresponding matrix representation? Yeah, any questions?
Sir, I have a question.
Yeah, go ahead.
I mean, if we would have defined this by G applied on V instead of VG inverse,
yeah,
then also it would have been.
Then also it would have been a homomorphism. You're right. Perfect. That's a good point. So that's not the regular representation. That is not the regular representation. Of course, there's a matter of definition. This one is defined to, so you are right about this. That is, if you had defined, say, some L tilde G, first, if you had defined L tilde G acting on V to be VG, this would not work. That's easy to see, right?
Yes.
Well, okay. But if you had defined L double tilde G acting on V to be GV, this at least will be a homomorphism. So this will work at least as far as asking for a homomorphism is concerned. Okay. But this does not give you the regular representation, which is a matter of definition, of course. You have to choose one of them. One is chosen, the other one is not. And there is a reason for that. The reason is not very, well, not very compelling, in the sense that there's no natural reason why one should choose VG inverse and not GV. But you will soon see. that if you choose Vg inverse, you get a slightly nice way of representing the the matrices that we are going to talk about. They will come about in a slightly nice fashion. Although that's really not that great a reason for choosing one over the other. Okay. But I will urge you to think of another reason why you don't really have two representations. You might say, I've chosen this one as a regular representation, I've ignored the other, which is fine. But you should also worry about what happens, why can't we have two regular representations, or one regular, one some other name representation of the same dimension, which automatically comes with the group? Why are we ignoring one completely? The answer to that you should be able to give me after we cover the next topic. Okay? So just wait
Since
for a while.
they will be similar only.
Yeah, there will be equivalent representations. You're right. These two representations will not be different. Just hold on. I will have a call. Shobhit, oops. Okay, let me put you on mute and for the time being. Hope I can find out how to. Yeah. Okay, sorry for leaving you here. I hope you are still here. I can see you are, but are you? Ah,
Yes, sir.
okay, let me just quickly drop off a mail to somebody now. Oh, yeah, I will do that after the class. Anyway, doesn't matter. Okay, let's coming back to this. So you get two possible regular representations. You don't talk of both of them because they turn out to be equivalent representations. Only one of them really counts. And by convention, we choose this one, that LGV is VG inverse. Now, how do I go to the matrix representation from here? You need to, of course, start with the basis. So basis, remember, is given by G1, G2, G3, etc. So some GI. So this is GI inverse. And you should be able to expand this GI inverse in the basis. Right? So you have a basis made out of the elements G1, G2, G3, Gn. Of course, this G that I'm talking about here, this G is one of the G1, G2, G3, Gns, right? This is a group element. And I'm hitting GI with G inverse. Okay? Now, can you tell me what kind of numbers I will get in the expansion? When I expand GI G inverse in the basis, what are the kind of numbers I'm going to get? Of course, this result will have to give me, yeah, go ahead.
The right cosets of GI.
What? Sorry, I think you're making it more complicated. GI is a single group element. G is a group element. So when I do GI,
Oh yeah.
of course, what I have to get by definition is the JIth element of the regular representation for this DG, or regular representation DG, acting on GJ, not acting on GJ, multiplying GJ. These are just numbers, right? J equal to 1 to n. This is what you are supposed to get. This is okay. This has nothing to do with the regular representation. This is what you will always get. An operator acting on a basis vector can be expanded in the basis vectors, and the coefficients, of course, form the representation matrix. But I'm asking you, what can you say about these numbers that are going to sit here? One thing you can immediately say, which is
Every column will have only 1, 1 and other element 0.
right, because G inverse will have to be a group element, right? It has to be one of these elements. Nothing else. GI is an element of the group. G is an element of the group, right? G is one of those G1, G2, Gns. So, although we have talked about this group algebra and a vector space, which is some linear combination of all the G's and so on, right now I'm just talking of LG acting on a basis vector. And LG acting on the, by the way, this LG is defined only for group elements. It's not defined for algebra elements in general, because algebra elements don't have inverses necessarily. Only group elements have inverses. So LG GI is GI inverse, and that's one of the group elements. And because it's one of the group elements, when you expand it out in the basis, the expansion will be a lot of zeros, a whole lot of zeros, only one somewhere, whichever element you have. So if GI inverse is GK, some group element, right? Then this has to be GK, and that means DJI regular, sorry, not inverse, where did I get the inverse from? The regular representation DJI of G will be delta JK. Okay, regular representation is the whole matrix, but the GIth element of that will be delta JK, where G is GI sorry, G is GK inverse GI, right? Is that okay? Clear? Or do I need to repeat this? This element has to be one of the group elements, and so when you expand this out, you will have only one, the one corresponding to that particular basis element. Everything else will be 0. And which element will be that? GK is actually just GIG inverse, or you can write G as GK inverse GI. There's a reason why I'm writing this form, which this is a form which makes it very easy to write down the regular representation. Well, all you have to do is write down the multiplication table. Like say, with our group, the group S3 or the group of symmetries of an equilateral triangle, all I have to do is just write down the multiplication table with a twist. The twist is, I will label the columns of the multiplication table by the group elements in some order, the basic standard order, E, A, B, C, D, F right now. But the rows will be labeled here not by E, A, B, C, D, F, but by E inverse, B, A inverse, B inverse, C inverse, and so on. Or using the fact that E, A, B, C are their own inverses. Okay, right? You can always do that, right? If there's no absolute rule that the rows and columns have to be labeled in the same order. Is that okay? You understand the procedure? You just writing down the multiplication table with the columns labeled, columns meaning labeling being here. These are the labels for each column. These are the group elements in whatever order you have chosen. And these are the inverses of the same group elements respectively. And now you fill up the multiplication table. Of course, the full multiplication table will take a lot of effort to do, but some of it can be easily done. This one is easy. And the diagonal is particularly easy in this case, right? The way I have put this down, the diagonals have to be identity because that's exactly how you put the columns and rows together, right? Is that okay? And then here you will put in AB, here you will put in AC, AD, AF, and so on, and fill up the whole table. Now, what good is that? Can anybody now tell me why did I do this? What will this achieve for me? In terms of the regular representation. It's all written down right in this part of the screen. Yeah? Well, if I want to find out the matrix D regular G, all I have to do is going to be an n by n matrix. Say suppose I wanted to do it for A. All I will have to do is just put ones wherever A's appear. And zeros everywhere else. That's it. You see why? GK inverse GI. This is how you have made the. You are asking if G is GK inverse GI, then the matrix element is delta JK, right? So what I've done here is I've just put in GK inverses here. GI is here, and if you multiply them together and get a G, that gives you the 1 in your regular matrix. There's just this thing translated. Is this okay? I'm still here, right? So even if you don't understand something, you should say you don't. I'm getting really scared that I'm not really here, and all of you are either, of course, all of you may have gone to sleep, which is possible.
Yes, sir, we can hear you.
You can hear us, but I can't hear you. The question is this understandable? This procedure for finding the regular representation matrices? Once again, I can't hear any of you saying either yes or no.
Yes, sir.
Okay, so if it is, then you can at least see one thing. And in fact, the regular representation happens to be a very, very important representation for theoretical purposes, for the purposes of characterizing all possible irreducible representations, despite the fact that it is not an irreducible representation itself. What irreducible representations are, of course, is something we have not discussed yet in this class, although I'm pretty sure most of you remember what they are from your previous exposure to this. But if you remember, at least when we talked about irreducible representations and stuff like that, we talked about the characters a lot, and the trace of the representation matrices. Now, in this case at least, so I'm going to introduce characters formally later, but at least right now I can easily write down the character or the trace of the representation matrices for the regular representation very easily. What is it going to be? Character, remember, is just the sum of the diagonal elements. Now there are 6 matrices, 6 groups here, group elements here. So each group element, of course, has its own 6 by 6 matrix. But one thing you can say for sure, if you have if you're talking of either A, B, C, F, or D, for none of them will there be a single non-zero element on the diagonal, right? If you look at the matrix, all you do is take a look at the multiplication table, and wherever the group element A appears in the multiplication table, you replace it by 1. The one thing cannot, even not one thing, only one thing appears on the diagonal in the multiplication table, which is the identity, right? Because that's the only thing which has to go there. Nothing else can. Is it okay? The way we wrote down the multiplication table with elements, group elements along labeling the columns and inverses of those elements labeling the rows, that made it automatic that the diagonal elements can only be E, can't be anything else. Is that clear? Okay. And since that is the case, then what is the trace for any of these? It's going to be 0, because all the diagonal elements will have to be 0, as long as the group element is not E. And if it's E, it has to be N. Is that okay? I can't be sure whether I'm getting across at all. So I'm assuming that the silence means that you're following this. This is going to be a very important result for us, that in the regular representation, the character for corresponding to a particular group element, which is just a trace of the matrix, is very, very simple to find out. It's N for G equal to E and 0 for G not equal to E. In fact, this will tell us later that the regular representation is reducible. Not only is it reducible, it actually contains all the possible irreducible representations a group may have. Not only that, it will tell you that it contains all the irreducible representations as many times as the dimensions, and which will automatically give rise to this very important result for us, that if you added the squares of the dimensions of every one of the irreducible representations, all the possible irreducible representations, you have to get n, which actually will tell you a huge amount of the possible irreps that you can have. Yes? Will somebody enter or leave or say something? Okay, Anuran said his connection is very bad. Okay, well, my connection is very bad today too, although thankfully I have not been thrown out after the very first time. Okay, so is this clear to everybody so far? Or if it's not clear, this is an important result, we will need it. So it's important to be clear as to whether this has been explained properly.
This property of this character wouldn't have followed if we have followed the other convention of defining the representation by G applied on V. So
Yeah,
if
wouldn't
given
have? Wouldn't it? Are you sure?
that time in the diagonal there will be elements other
No, let's
than.
see. Then you are defining LG acting on GI then, not as GIG inverse, but as GGI. But this will also be some group element, right? Has to be. Is it okay?
Yes. So I
Has to be some
remember
GK.
character but doesn't depend on the I mean all of the equivalent representations
Yeah.
have the same
So
character.
that, from that you should have known that what you are saying will not work. G is GK GI inverse, right? If the two representations are actually equivalent, the way said we have said that they should be, but if they really are, then G equal to GK GI inverse is what you will get here. Then they should have the same characters, right? Characters will not change if you go from one equivalent representation to another. The matrices may change, but the character will not. So here G is given by GK GI inverse, and to form the representation now, what you will have to do is essentially take the the elements in order here, E, A, B, C, D, F, the standard order down the labeling each one of the rows, and the non-standard order labeling the columns. Is that okay? And then notice that if you multiply this, the element G actually goes and sits at wherever GK G1 inverse is. And if you do that, again, you will get only E's down the diagonal. Right?
Yes, I get
You
it
have to.
now.
And so, once again, even for, so the point is, if we are claiming that there are similar representations, which you should be able to show without actually going through this, which you should be able to show directly. But if they are similar representations, they have to have the same character. So chi regular G has, even for this, say let's call this regular tilde G, will also have to be the same, n or 0. So that will not change. It's just one of them which you take by convention. That's it. No, well, maybe the convention, I'm not sure why this is the convention, not the other one. But maybe the convention is simply because this leaves the more obvious labeling. This one, for example, you have to label the columns in the non-standard order, not in the basis order, but in the order of their inverses. Now that's of course, here the columns are labeled the wrong way, the rows are labeled the right way. In the way we did it, the columns are labeled right, the rows are labeled wrong. And then maybe if you look at the multiplication table, the first thing that catches your eye is the column heading, because that's the one which We are used to reading from left to right, not top to bottom. So if you had a labeling here, this is the one which should catch your eye first. Maybe that is the reason why you want to keep that in the right order. And that's why you define it that way. I'm just speculating. That may not be the case. My whole point is there is no mathematical reason for choosing one over the other. But you have to choose one. You can't have both of them. That would be an overkill. And taking both of them does not give you any extra information. So just use one, whichever. So I'm just trying to give you a possible reason why this is the one which you used. Okay. Do I need to explain to you what an equivalent representation is? That is, we have already been talking about equivalent representations quite a lot. I hope everybody remembers what an equivalent representation is, right? So I will fold up. I'm taking that for assent. I'm taking assent in the sense that I don't have to explain what an equivalent representation is. So then we are going to move on and talk about a special class of representations which are going to be very useful for proving various results. These are called unitary representations. A representation T where every one of the representation operators Tg is unitary for all G. And what is a unitary operator? You all know this, but for a unitary operator to exist, you first have to have a what is called inner product available or scalar product available, and that helps us to define T dagger as that operator which acting on V, inner product with W is the same as V's inner product with TW, and a unitary operator is one for which T dagger T and TT dagger is identity. This is of course elementary linear algebra, and all of you have done enough quantum mechanics to have heard about unitary operators over and over again. So that's straightforward. The reason why we are talking about this is that there is a theorem. The theorem is every representation of a finite group G on a matrix space. So the important thing is, in order to be able to talk of unitary representations at all, the underlying vector space on which the representation is sitting has to have an inner product defined, so it has to be a metric space, right? Every inner product automatically defines a metric. Actually, strictly speaking, we generally don't demand a metric space. All we demand is an inner product space. So a given representation on V may not be unitary. The matrices involved may not be unitary, but you can always find an equivalent representation in which every matrix is a unitary matrix, or every transformation operator is a unitary transformation operator. So is the theorem clear to everybody? This theorem happens to be very, very important because we will see that several results can be proven very easily for unitary representations. And the fact that no matter what your representation is, as long as you're dealing with a finite group, you can always find a unitary representation which is equivalent to that, helps you to prove many, many results very easily. So how do you prove this particular theorem? And the reason why I'm talking about the proof of this particular theorem is that first of all, this theorem is itself important, but more importantly, this actually sort of demonstrates a technique that's very useful in finding out many results in group theory. The technique will be used over and over again. So this essentially goes this way. You have some representation, let's call that LG. There is not necessarily unitary representation, but what you can do is use this to form a particular operator, which is LG. By the way, I'm saying operator because in my to my thinking, L of G is an operator acting on a vector space, but you can sort of mentally substitute each statement I'm making with a matrix if you are thinking of the matrix representation, and it will sort of follow through. The result will follow. You take the operator LG dagger LG and sum up over all possible G. And this is, by the way, this sum is of course perfectly well defined in the standard sense of the word. Operators can be added together. So, and this gives you a new operator X. Okay. Now this operator X has certain very special properties. One of them, of course, is this, right? I hope everybody can see that. Also, if V is not equal to 0, for all non-zero V, will be what? Can anybody tell me what this is going to be? What can you say about this? Not equal to necessarily, but what can you say about VXV? Okay, let's move on to the next page here. Using the linearity of the inner product, you can easily write this as V. Now, what's the next step?
Is it inner product of some other element with itself?
Yeah, it is the inner product of LGV with LGV, right?
So it should be non-zero, I mean positive.
Non-zero or positive? Which one do you mean?
Positive.
Can't it be 0?
Because you assumed V not equal to 0.
Yeah, but V not equal to 0, why, what prevents LGV from being 0? I've assumed V not equal to 0, I agree. But what prevents LGV from, this is LGV's inner product with LGV. Of course, by the way, VXV is not an inner product of a vector with itself. VXV is the sum of a lot of inner products of vectors with themselves, right? That's not necessarily an inner product of a vector with itself. But each individual piece here is an inner product of a vector with itself. So each individual piece is definitely non-negative. Why can't it be 0? I agree that V is not 0.
Because L of G is invertible.
Exactly, because L of G has to be invertible. It's a representation after all. It is part of a representation after all. So since L of G is invertible, L of G V cannot be 0 if V is not 0. So that completes the proof that these are non-zero vectors. So each piece is positive, so the whole thing is positive. So VXV is what is called a positive definite operator. VXV is going to give you 0 only if V is 0, otherwise it's going to give you a positive number. Okay. Now for a Hermitian positive definite operator, we can immediately, okay, we will borrow some results which are basic results from linear algebra, but you have all learned about them several times in quantum mechanics, that you can write this X as this. Well, lambda is nothing but the eigenvalues of x, and these are the projection operators to the corresponding eigenspaces. By the way, what role does this play here, or this Hermitianity in this statement? This is really the spectral theorem that an operator can be decomposed this way. But why is Hermitianity important? If the x were not Hermitian, could we all still say this?
Hermitian operators are diagonalizable.
Exactly. So the point is that Hermitian, we can say this not only for Hermitian operators, we can actually say this for a whole bunch of other operators as well. But for Hermitian operators, we're guaranteed that we can say this because the projection operators actually are complete. That is, they span the entire space. And another way of saying that is Hermitian operators are diagonalizable. And what else can you say about this particular spectral representation?
The eigenvalues should be real.
The eigenvalues should be real. Good, but not only real, something else. Hermitianity will say eigenvalues are real. We'll also say p lambda prime is delta lambda lambda prime. P lambda, which is just the property of the projection operators. That these are really projection operators. I hope all of you know this stuff. If you don't know elementary linear algebra, I can explain it to you. You don't really need to go through all the basic stuff that you've learned all over again. But lambda has to be what? Real, fine. That's from the fact that x is Hermitian. But x is also positive definite. That means lambda is positive, all the lambdas. All the eigenvalues, because if you take an eigenvector v lambda and form this, what will you get? X acting on v lambda is nothing but lambda v lambda. So v lambda, x lambda v lambda. Take any eigenvector of x, this is what you're going to get, right? That's simply lambda. If you're assuming that the v lambda is normalizable, or even if not, is non-normalized, it's still positive, right? Because lambda is positive and v lambda inner product of course is positive. So all the eigenvalues have to be positive. Okay? Is it okay? So if that is the case, then we can easily define this operator. Let's call this S. All this talk about x being Hermitian and positive definite is essential to ensure that you can define a unique operator S this way, x to the power half, where, well, basically, if you think of the matrix x as a matrix, it's a diagonalizable matrix. S is the corresponding matrix with the eigenvalues are square roots of that matrix. Is it clear to everybody? Can of course always define this, and then you can easily check that S square, which is sum over all lambda to the half p lambda times sum over all lambda prime to the power half p lambda prime, is this. But using the fact that this is delta lambda prime, p lambda is easy to see that this result is sum over all lambda p lambda, which is x. Right? So S squared is x. So S is the square root of x. Okay. Is this the only matrix whose square is x? The answer is no. But this is a matrix whose square is x. Is that okay with everybody? Okay, I need a response here because I need to move on.
Yes, sir.
Okay, if it's not, you should actually speak up. Anyway, fine. So S square is X. Now what we do is do this. Take your matrix LG for any particular G, form this thing. Or no, I don't really want to form this because I want to show unitary, right? So not this one right now. Let's do this. Let's take LG's adjoint S square LG, and let's try seeing what this is. This, of course, is LG dagger sum over G prime belonging to G. I have to change the S square is X, so I can just put in X here, but I have to change the dummy index. That's all I did, right? Now you see that this becomes sum over G prime belonging to G. For a finite group, this interchange of summation and this multiplicative product as all of this is trivial. So you have LG dagger, LG prime dagger times LG prime LG. So this, of course, is LG prime G. The product of these two things in the back, right? But the first two things, LG dagger, LG prime dagger, in the opposite order, is actually the adjoint of these two, the product of these two. So LG prime G dagger. Is this okay? Now I'm going to claim that this is the same as X or S square. Can anybody see why? Or if you can't see why, tell me. This, by the way, is a standard step that I'm going to follow over and over again in various proofs. That is, when you have a sum over the entire group. Now you're changing the group element and you're summing over G prime and you're claiming that this is the same as X. Can you see why? In other words, I'm claiming the sum over some function of G okay, maybe I could call this G prime. I'm making this claim where G is any element of the group. So I have some function of the group elements, I'm summing up over all the group elements, and that sum stays the same if instead of summing up over f of G prime, I'm summing up f of G prime. Why is that the case? So why is that the case? That's a question. So I need an answer. Can anybody tell me why this has to be true?
It follows
From
theorem.
which theorem?
Rearrangement theorem.
Yeah, sorry, I couldn't hear the rearrangement first time around. So it is really nothing but the rearrangement theorem, which guarantees that all of the terms that you see in this sum are the same as the terms in this sum, except in a different order, perhaps. I said perhaps because one of the elements could have been the identity, G could have been the identity, in which case, of course, they will be exactly in the same order. But in general, they're in some other order. So what we have established here is this. For any group element LG, LG dagger S square LG is S square. So how does that help? Well, it helps you to establish this S inverse. Now, How do I know that S has an inverse? That's important. S, remember, S square is defined to be X and S is defined to be. So what are the yeah?
If we take the diagonal elements to be 1 by root lambda.
Yeah, you can. That would be if you diagonalized it. But more okay, that's correct. However, one easy way of seeing even without calculating the S inverse, because we are not really trying to calculate things. All I need to do is establish that S inverse exists. The easiest thing to say here is, since X was positive definite, all the eigenvalues were positive, right? So none of them were 0. That's important. So none of the eigenvalues of S, for example, the halves, are 0. So S has to be invertible. An non-invertible matrix has a 0 eigenvalue, right? This one doesn't. So S inverse exists, and then you end up with, and not only does S inverse exist, there's another step which I didn't talk about, which I should have. It's easy to see that S adjoint is S. That simply follows from the fact that all the lambda to the halves are real. That is, of course, because all the lambdas are positive. So now you see, this is LG dagger S LG S inverse equal to identity, right? I just written this expression with bringing one S on this side, the other S on this side. But now you see that now I have these operators, which we can call L prime G. Now I don't really need to tell you, because everybody told me that equivalent representations you understand. This, of course, this L prime G is an equivalent representation to LG, right? And S is the matrix which makes you go from one representation to the other. Is that okay? But notice that what is this? S inverse LG dagger S is the adjoint of, is also of course the same as S dagger LG dagger S, because S is Hermitian. Sorry, what did I do? No, that's not right. Sorry, but this is the same as, if you take its adjoint, what do you get? You get S dagger LG S inverse dagger. But S dagger is S, right? LG and S inverse dagger is S inverse. So what we end up with is the adjoint of this is L prime G. So now this relation that we derived, that S inverse LG dagger S LG inverse S, is nothing but L prime G's adjoint times L prime G is identity. Remember, this works for all G. So for all G, you have now found a new representation. You have started with a representation LG, which was not necessarily unitary, but now you have this new representation L prime G S LG S inverse, and L prime G is unitary for all G. Therefore, what we have established is our theorem, the theorem which said every representation of finite group G on a metric space, on an inner product space V, is equivalent to a unitary representation on V. And what we have done here is we have shown you how to arrive at that equivalent unitary representation. Now, the most important step in this whole proof is simply this thing. This step here, where we had an original sum, now you have a sum over different elements, but you are claiming that this sum is the same as this original sum, which of course uses this basic idea, which is the consequence of the rearrangement theorem. Now this of course works for finite groups, For infinite groups, you may have run into trouble. For finite groups, it's easy to see that if you rearrange the terms, the sum doesn't change. Because it's a finite sum, rearrangement will not change the sum. But you all know that if it's an infinite sum, then things become a bit more tricky. Of course, after all, an infinite sum, of course, has to be defined as a limit of a sequence of partial sums and so on. And there often, I hope everybody knows the Riemann rearrangement theorem, right? Or the result about this Riemann's proof. That, okay, this is not really Riemann's proof, this is just one application of that. How much is the sum, by the way? Anybody? 1 minus half plus 1/3 minus 1/4 plus 1/5, of course. Then minus 1/6 and so on. Anybody remember how much the sum is?
Natural logarithm of 2.
Yeah, this is log of 2. If you add it up, you will get log of 2, but this is a very, very slowly converging sequence and all that, but that's a different story altogether. It does converge. It's a conditionally convergent sum because 1 plus half plus 1/3 plus 1/4 plus 1/5. The moduli, if you add them together, they don't converge. Okay. And Riemann's theorem essentially says that you can rearrange the terms of this particular series to sum it up to anything you want. So log 2 is the sum if you have 1 minus half plus 1/3 minus 1/4 plus 1/5 in this order. But if you allow rearrangements, then there's no guarantee what the sum is going to be. Or rather, there is a guarantee that you can make it add up to any number you want. You want it to add up to 1, you can do that. Want it to add up to 10, doable. You know the theorem. Everybody?
No, sir, I didn't know.
Okay, so let me just quickly tell you why this works. It's easy to see. If you took just the positive terms and just the negative terms, so the ones which come, sorry, 1/3, I made a mistake here because this is not in the positive terms. Just took the positive terms 1, 1/3, 1/5, 1/7, and so on, and just the negative terms. Both of these would diverge, right?
Yes, sir.
Pretty easy to see. So suppose I want the sum to come out to be 10. All I can do is keep on adding the positive terms and keep on going until the sum exceeds 10. Right? The sum will exceed 10 at some point, right? Because the sum is infinite. The sum of all the terms is infinite. It diverges. So if I keep on adding terms more of one after the others, at one point, the series will go beyond 10, right? But once it does that, I will immediately switch to the negative terms and I will bring in the minus half. And I will bring in as many negative terms as needed to go below 10. Again, because the negative terms themselves add up to minus infinity, or the moduli add up to plus infinity, I can actually do this, right? So I can go just below minus 10. And then, once I just go below minus 10, I will then start with the other terms that were left in the positive series. I've used up some of them, now use the rest until you go above plus 10. Then take the negative terms again, go below minus 10. And by doing this, it's guaranteed that you will stay arbitrarily close to, and since the terms get smaller and smaller as you go by, you can get closer and closer to 10 as you go by. So the result is you can prove explicitly that this is going to work out. This is any sum you want, you can get. What that of course means that infinite sums are tricky things, and that is why infinite groups are actually more tricky to handle than finite groups. Okay, infinite groups are trickier, and there happened to be a special case of infinite groups called compact groups, which essentially is a term which comes from topology. We will see why compact groups are so useful, because they actually help you to basically treat sums as if they were finite sums and essentially do many of these calculations which you take for granted with finite sums also over there. So the basic trick in group representation theory, the one we have used right now, this basic trick is going to work even for infinite groups, provided the infinite groups have some extra restrictions on them. It will not work for all infinite groups, which is why we are so, when we deal with infinite groups, we look for compact groups more often because they are easier to handle. Okay, anyway, I have to go now. I am all out of time, and moreover, my wife has a class right now, and she needs this space, not by computer, but at least a space. Okay, so I will stop recording now, and I just have one question to